So here's what I think is the cooler part of the integral test, specifically as a convergence test. We really want to exploit more of the fact that the sum of this bunch of integers should really be very similar in some ways to the integral of this real valued function, which sometimes we can get an exact answer for. And the way we do that, and this is a very natural thing, and this should be no surprise to my students because we've talked a fair amount about error estimates and remainders, is that if we call this S the actual sum, right, we can look at what we can calculate in a very low-tech way is the nth partial sum of this guy. 2 to n. Ooh, let's see. See, here's where I need a dummy variable. This is why I like using k for the variable. So the cube of the log of k here. Okay. Or in other words, just 1 over 2 log cube 2 plus dot 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 plus 1 over n log cube n. That's cube. This is going to give us some estimation because we know now that we know it's convergent, we know that eventually this gets as close as you want to s to the actual sum s. But how fast does it converge? It might converge very slowly. And so what we want to know is what's the remainder. That is what's left over if you give me the explicit sum up to 100 or 1,000 or 1,000,000, and I want to know what would I have to add to it to get this hypothetical exact sum, which I'm probably never going to exactly get precisely. Okay, so I want to get some bounds on this. Usually, most estimates are just a bound on the size of this thing, and just say, well, it can be at least, it's at least minus 0.2 and less than 0.2, something like that. But it's interesting what the integral test gives us. It gives us a real window, and it actually says that it's going to be less than or equal to something and greater than or equal to something. It's going to say that this guy is pretty good, but no more than that. And so let me make that explicit, and let me do it in this example with this particular a sub n, right? But it's going to be very general. So we want to get a bound on the difference here. So that difference is just the sum of what would happen if somebody else went and summed all the rest of the terms off to infinity. And you know what? The picture we did for the convergence test for the integrals is really, really similar. It provides a really, really similar picture of what's going on here. So, and the fact that there was a left endpoint method and a right endpoint method is going to give us two statements about Rn, which is really cool. So, let's look at this this picture. This is a a right endpoint picture. Okay, and so what have we done? We've got a sub n plus 1. That's equal to f of n plus 1, and so that's going to be that height, and so that times 1 is exactly a sub n plus 1. Sorry, it doesn't fit very well. Let me put it here. A sub n plus 2 is the area of this rectangle because I've synced it up so that f of n plus 2 is the height, and then that times 1. This guy has area a sub n plus 3, etc. So guess what? There's the sum. There's exactly that sum, which is exactly the remainder, and it is less than or equal to this integral. So we get that Rn is less than or equal to the integral from n to infinity of f of x dx. Well, and I'm going to make it explicit. Okay, and the cool thing is that now this is going to be much more useful than like the number we got for like the integral from 2 to infinity, because this is going to be fairly small. And we're not saying it's exactly equal to what's left over, but it's going to be a bound on what's left over, and it's going to be fairly small, and that is going to be actually useful. Okay, so usually you would just say, okay, that's as big as the error can be, and for all I know, the error could be really, really small. I could be really lucky, and I might never know, and the error is actually really, really tinier than this. But here's where the other version of this picture comes in. Let me just rewrite a little bit. It actually tells us, it gives us a lower bound on the remainder, and tells us, no, it actually can't be that great. So here is where we do a left endpoint sync up. Okay, but at n plus 1, so actually start it here. Okay, because I still need it to talk about this exact sum. And if I switch from right endpoint to left endpoint, there's going to be a shift over. So I have to counteract that. Okay, so now I draw the same rectangle. These are the same rectangles, really, but just synced up in a different way with the picture. There, again, is a rectangle of height f of n plus 1, which is a sub n plus 1, and times 1 width, so that's a sub n plus 1. And again, they don't quite fit. That's a sub n plus 2. That's of a sub n plus 3, etc. But now they're on top. Okay. And so notice what we've got is that the r sub n, it's still exactly this. That is bigger than an integral. You might be like, well, how could it be bigger than and smaller than the same thing? It's not the same thing anymore. What I'm comparing it to is the integral from n plus 1 to infinity. And this is really cool. We're going to be able to, in some cases, like this one, we're going to be able to get an exact formula for this quantity and an exact formula for this quantity. And that tells us that the error that we've got between our low-tech, let's just add these up to like 100, and I'll do 100 in a second, the error between that and the real thing is constrained. And sometimes it's going to be pretty tightly constrained. And that actually leads to a really nice trick that you can do. So let me show you. Let's see. I'm going to go over to Scientific Workplace, and I think I have the window too big. Let's make that window a little smaller so we can see what the heck's going on. I don't think I forgot to resize everything. Okay, that's pretty good. Okay, so here with Scientific Workplace, what do we got? We've got S is this idealized infinite sum. We're never going to really nail that down. There's F, okay? And now we just do the same kind of integral we did before, but we take it from n, and then we're going to plug in n plus 1 in a second. The integral from n to infinity of this guy, similar to what I did before, I guess without the explicit change of variables, but you've seen sort of the idea before. It's minus 1 over 2 times the square of the log of x from n to infinity. As the variable goes to infinity, log goes to infinity, 1 over goes to 0, so that doesn't evaluate to anything. Then minus a minus, 1 over 2 log squared n. So it's a reasonably nice formula. Okay, so here's what the remainder estimate gives us. The mystery remainder, what's going to be left over if we sum up to n, is between 1 over 2 log squared n and 1 over 2 log squared n plus 1. So a good way to say that is, remember r sub n, that is, just to have it one more time, it's what I need to add to s sub n to get s, ideally. And so we can just rewrite that and then say, hey, I want a statement about S. I know I'm not going to get a precise statement, but I want a statement that bounds S, this mystery quantity that I'd love to have a handle on. So what this says, I'm just adding S sub n to all three quantities. It says that it's no more than an explicit up to n sum, and we're going to do up to 100 in a second, plus this upper bound on the remainder, but it's at least that S sub n plus the lower bound. Oh, stop that. Plus the lower bound on the remainder. And this is a fairly uncommon kind of situation. Again, what I'm saying is that we're going to think of this as our first estimate for S. Kind of by definition, that's what it's supposed to be. But it says you've got to add at least this much, and it's a very well-defined quantity, it's a precise formula, to get nearer to the actual sum. That's pretty cool. The idea, I guess another way to say this idea is that we know that when we stop at like S sub 100 here, like this guy, we know we're missing something, especially if we've got a sequence of positive terms. We know it's an underestimate because we haven't added 101, 102, etc. And it would be really nice to get at least some rough idea of how much we're missing. And this is exactly what that does. Okay, so here I just had the computer actually add up, very low tech, but it would be very laborious to do by hand, all these terms from 2 to 100. Not really very hard for a calculator or computer to do. Your TI calculator, for example, will do that. So you get about 2.042361. And again, we know that the real sum, if I added 101, 102, 103, it's going to be a bit more. And now we've got a handle on roughly how much more it's going to be. So I'm just writing down this formula here, okay? And you're going to have 1 over 2 log squared 100 and 1 over 2 log squared 101. And a cool thing about this particular example is that those are pretty similar to each other. So we know that at worst, you're going to add in 0.023576. Great. So at most, S is going to be this guy. But it also tells us that you're going to add at least 1 over 2 log squared 101, which is a pretty similar number. And that's an estimate of all those missing rectangles that we chose not to include. So it turns out to be these numbers. You can read those. I don't need to read the digits to you. But the main thing is that those are really, really close to each other. And they're much closer to each other than they're close to 2.04. So if we had just stopped and said, hey, 2.04, 2.042 is our estimate, and I know that that's not perfect, but how am I possibly going to give you a better estimate than just a finite partial sum? Well, guess what? A better estimate is either of these two numbers, or if you want to be clever, slightly clever, average them together. I'm not claiming that this is S exactly. Notice the approximately. But if you average them together, that's probably the best guess given these two numbers. And then you can say, I also took the difference, half of the difference between these two as well, and it turns out to be 0.00005. And you can say that S is approximately this number in the middle of that error range, plus or minus this error bound. And this is a very sharp thing. You can say for sure that S is between 2.0658865 minus and 2.0658865 plus. And that's really sweet. That is substantially better than what we had just by S100. And we didn't have to add even a single explicit more term in there. Somebody else could maybe add up to 1,000. But it's cool that you stop at 100 in terms of your actual summing up the sequence. You do a little calculus and look at this integral test estimate, and it's as if you summed up a lot more terms, but in a cleverer way.